Hello everyone. We'll discuss about notches and weirs. That is second part of your module number 4. There are different types of notches and what for they are used. What are weirs, how they are different from notches, and then how to calculate the required discharge through them. That is what we are going to discuss in this session. Okay, module number 4 has got syllabus, orifice and mouthpieces. We have finished it. Now what is left is notches and weirs. We'll do all this up to trapezoidal notch, triangular notches. Till that we'll finish today, now in this session. The remaining will be in the next sessions. Okay. Here in the cross section of the notch there will be a plate or a wall. What you are seeing is section. Actually the plate will be in this manner. Actually, if you just try to see, this edge is being seen there, this beveled edge, and you will have this point like that. So this is nothing but in this manner. There is a plate across a channel, right? So that makes what is known as notch. It will be having a different shape, maybe a cut rectangular shape, maybe a triangular shape. There are a variety of things that you will study in further slides. So I'll take it off. So this is what is notch cross section. So there is a plate with a beveled edge, and then you can just see the flow also. The flow is in such a manner that it is in least contact area. It is not the other way around, right? So that when the jet or the water comes out as a sheet, it will be touching minimum cross-sectional area of the notch. Okay, so this tip is known as sill, and this sheet of water what comes from the top is known as nappe. So this is notch, and then here there is a weir. Weir is made up of masonry structure or concrete structure. Obviously it will be huge in size compared to notch. Notch and all, you can use it across a very small channels, maybe less than a meter or so. Yeah, I mean by less than a meter, around 30 centimeter, 40, 50, 60, 70, 80 centimeter, like that. If it gets bigger and bigger, like maybe a stream, across a stream, if you want to find the discharge, then you have to have what is known as weir. Okay. Anyway, what is notch and weir we'll see. A notch is a device used for measuring the rate of flow of liquid through a small channel or a tank. Yeah, here this is important. Small channel. I told you the range. Something like less than a meter. If the width of the channel is, you can use it. Notch is a cut on the side of a measuring tank, generally made up of metal sheet. So this will be made up of a metal sheet. A weir is a concrete or a masonry structure placed in an open channel over which the flow occurs. Right? The flow is coming full, but because of the obstruction of this weir, the flow only goes on the top, right? So it is generally in the form of vertical wall or with bell shape, right? Maybe just a perfect rectangular cross-sectional shape would be there, or it will be a smooth shape like this, which is called as technically ogee shape, or it is a bell shape, right? Okay. Now this sheet of water which goes above the sill, it is like a sheet of water. The sheet of water flowing over a notch or a weir is known as nappe. Obviously this is free nappe, which is not clinging to the notch or weir, whereas weir, here in this weir, the nappe is touching the structure. So this is called clinging nappe. The nappe is in touch with the weir. That's why it is called clinging, and this is free nappe. Okay. Then the bottom edge of the opening is known as sill. This is bottom because it is a niche or a cut, it is a bottom, right? So this is called also crest or sill, right? That particular edge over which the water jumps out is known as sill. Okay, here I have shown a channel in which the water is flowing, right? So you can assume that those arrows are indicating water flow. Now there is classification of notches according to the shape of the opening. It is a rectangular notch or a triangular notch or a trapezoidal notch and a step notch. We'll see here there is a channel which is flowing, and then let us insert a plate, right? Now when you insert a plate, obviously the flow will be obstructed. You have to have a cut in the plate, right? What you have to observe here is from the bottom up to that level is the water level inside the channel. The plate size is slightly taller than the edge of the channel itself, right? If we cut different shapes into this, they make what are known as notches. We'll see them, right? So this is the same plate is taken, and then we have made a cut in the shape of a rectangle, so it becomes rectangular notch. If I cut a shape of V or triangle over here, right, it will become triangular notch or V notch. And then if I cut a shape of trapezium, obviously trapezium will have lesser width at the bottom, larger width at the top, and almost all the time it is symmetrical unless it is told. Most of the time, 99% it will be symmetrical, right? Even this is also symmetrical. Obviously rectangle is symmetrical. Then you can have stepped cut like that, stepped notch. So and then water will be coming like a sheet. So when it comes out only this much, but actually the water is flowing for full width of the channel and full height, right? So actual cross-sectional area of the flow, when it is moving inside, it will be having this much. All this is a flow cross-sectional area. So if the above the crust, if the height is termed as generally h, and then crust height itself is termed as z or z, the total depth of the water that is flowing inside the channel will be h plus z or h plus z, the total depth of the water that is flowing. And here the length of the rectangular channel is termed as this. So this width is known as length of rectangular channel and indicated by the letter capital L. Here it will be, this is the crust and half the angle is always specified, or this whole angle is specified. Here crust length L as well as the angle is specified. So you have to mention about theta as well as you have to mention about L. In this case it is only theta by 2 and theta by 2, the whole angle is theta. Here of course you should mention everything like this height, this width, this height, this width, and so on, right? So we are interested in these three, that is rectangle, triangle, and then trapezoidal notches. So here the depth of the flow is h plus z, width of the flow will be this whole width. If we call it as L, the total width of the channel is taken as L. The flow occurs with a cross-sectional area L into bracket h plus z. So this is the total cross-sectional area of the flow, but when it comes out with only h into this L, right? So cross-sectional area of flow, when it comes out as an nappe, it will be having h into L, whereas actually the flow occurs in the channel with L into h plus z, right? Okay. Next we'll see the same rectangular channel I have taken, and as I have told you, this is h, right? This is z, and this I have called it as L, this much, and this one I have called it as L. Okay, now according to the effect of sides on the nappe, so when the sheet of water comes out, obviously the sheet will not be having a width equal to L, because the side will be pushing it out slightly. The sheet of water will be like that, and then on this side also it comes slightly inside and it will be like this. So the sectional area, the cross sectional area will not be simply h into L, it will be slightly less because of end. There is a vertical edge which is called end, right? Because of this end there will be a contraction of the cross sectional of the flow. That's why this is called end contraction. So that's why here it is highlighted notch with end contraction. How many end contractions are there? There is one here, there is one here. There are two end contractions in this case, right? Now suppose if you have a rectangular notch which will be having a crust, that is this crust, which will be equal to the width of the channel itself, then there is no question of end contraction. In that case it is called notch without end contraction, or it is also termed as suppressed notch, means end contractions are suppressed. We'll see it in the next figure. Look at that. This is side of the channel, but the crust is now equal to, the crust length is equal to width of the channel itself. Because of that there is no end contraction. So here if you see, the water will be flowing right up to this width. Suppose if I draw a sheet of water, it will be flowing like that at the end, and here it will be flowing like that. So there is no end contraction. This sheet comes as it is. This sheet comes as it is. There is no end contraction, right? So such case is known as suppressed notch or suppressed weir. A notch without end contraction is known as suppressed weir. Okay, now how to calculate the discharge? Here in the figure I have drawn a rectangular notch. The length of the notch is shown as L, you can just see here, and then the head over the crust, this is crust or sill, head over the crust is H. Of course there will be water all everywhere here, but when it comes out as a sheet, as an nappe, right? So head over the crust is capital H. Okay, now the cross sectional area of the notch, of the flow, will be L into this whole height, which is known as capital H. But for the sake of analysis, we'll consider at a depth H, lowercase letter, a small width of dH of length L. Consider a sharp edge rectangular notch with a crest horizontal and normal to the direction of the flow. Yeah, for the direction of the flow this is perfectly normal. H is head of water over the crust, L is the length of the notch or weir. Consider an elementary horizontal strip, that this dark strip that is shown here, of length L at a depth H from the surface of the water as shown in figure. The cross-sectional area of the strip becomes L into dH. L is the length, dH is the width, so cross-sectional area would be LDH. Now if you have got a depth of H, when the water comes out, it will be having a velocity which is equal to root 2 GH, right? So theoretical velocity of the flow through the strip is root 2 GH. Now the discharge dQ, which is coming through this dark strip, dQ will be equal to the coefficient of discharge, right, multiplied by area of the strip multiplied by theoretical velocity. So CD, area of the strip, becomes L into dH. You know that it is L into small dH. Theoretical velocity is root 2 GH. So CD becomes coefficient of discharge. Now we have to integrate this expression from 0, 0 at that level up to capital H, right? So we'll do that here. Okay, the total discharge Q for the whole notch or a weir is given by, or weir is given by it is given by integrating the above equation between 0 to H. So integrating from 0 to H, CDL root 2GH DH. CDL are constants, root 2G is a constant. So because of that, it has been put out of integration sign. 0 to H, H raised to half DH. So constants, H raised to half plus 1 divided by half plus 1, 0 to H. So this becomes H raised to 3 by 2, 0 to H. This becomes 1 and half, actually it is 3 by 2 here. There is a mistake. So this is, it should have been 3 by 2. So it becomes 2 by 3, and this becomes H raised to 3 by 2 minus 0, that is H raised to 3 by 2. So the discharge through rectangular notch is given by this equation 2 by 3 CD L root 2G H raised to 3 by 2. This simple expression will help you in solving many problems. Okay, we'll continue. This is rectangular notch. Now next is triangular notch. You can just see here it is shown again symmetrical, right, with theta as the whole angle or theta by 2 as half the angle. The crust is over here as a point O, and then head over the crust is capital H once again. And for analysis sake, we have considered at a depth this H having a width DH and across a length, let us say something like A to B or A to A to B. Now half of this is considered here AC 3 theta by 2 H minus H, because capital H minus H would be this height, H minus S. Now you can just see here the analysis. Discharge over triangular notch or weir is same as that. So let H be head of the water above the V notch. Theta is the angle of the notch. Consider horizontal strip of water thickness DH at a depth H from the free surface. Now tan theta by 2 would be AC divided by OC. AC by OC. AC we don't know. OC is H by H minus H. So because of that, this AC becomes H minus H into tan theta by 2. The whole strip AB is double that. Because of that, width of the strip AB is equal to 2 times AG, 2 times AC, that is to say 2 times H minus H tan theta by 2. Now you have determined AB. Now cross-sectional area of this strip AB will be AB multiplied by DH. So area of the strip will be 2 H minus H tan theta by 2 into DH, that is DH. The theoretical velocity of water through the strip will be equal to root 2GH. Because it is at a depth H, the velocity becomes root 2GH. Now this velocity, this cross-sectional area gives you a discharge dq. Okay. So now the discharge dq through the strip will be CD, coefficient of discharge, area of the strip 2 H minus H tan theta by 2, theoretical velocity root 2GH. Now for total discharge, again you have to integrate from 0 to capital H. So Q is equal to 0 to H, 2 CD H minus S tan theta by 2 under root 2GH DH. Now all these are constant factors taken out, 0 to H. Then this H minus H, this H raised to half multiplied H raised to half minus H raised to 3 by 2 DH. If you integrate, right? So what happens is this will be h raised to 3 by 2 divided by 3 by 2. This will be h raised to 5 by 2 by 5 by 2, 0 to h. Now if you substitute, it will become 2 by 3 h raised to 5 by 2 minus 2 by 5 h raised to 5 by 2. Simplifying, right, h raised to 5 by 2, h raised to 5 by 2, 2 by 3 minus 2 by 5 multiplied by 2 there, it will be 8 by 15. So the final expression for discharge, final expression for discharge through V notch is equal to 8 by 15 CD tan theta by 2 square root of root 2g h raised to 5 by 2, right? So this is discharge through triangular notch. Thank you. We'll stop here.